Hello students, in this video we'll consider the logarithm from the perspective of conformal mappings. So let's be given the principal branch of the logarithm. Namely, w equals the log of z is the log of the modulus of z, where that's the ordinary logarithm, plus I theta, where here theta, where theta is between negative pi and pi. So you make your branch cut on the imaginary, on the negative axis, right? So it says that your branch cut is on the negative real axis. Okay, good. Now, what's dw/dz? dw/dz, by definition of the logarithm, right, is 1 over z, and that's not equal to 0, but I cannot have z equal to being 0, right, for z, such that the imaginary part of z, such for all z, let's say for all z on the complex plane minus negative infinity to 0. You can't choose those points, right? Those are not on your branch cut, okay? Good, now let's examine the situation. So the question becomes, where am I going to map the slit complex plane? So question, log of z maps this slit complex plane onto what region? Okay, let's figure out what it does. All right, so here's our situation. Here's the complex plane, R, I, R. And here's our branch cut. Can't have those values. I'm asking the question though, what if I look at the whole complex plane aside from that what? Aside from that branch cut, like this, the whole complex plane. Where's the logarithm going to map this to? Okay, that's a good question. Okay, let's do it. And so, well, let's analyze this carefully. So let me be given any point z in C minus, okay, we can write z is equal to r e to the I theta, okay? And so therefore, where theta is between negative pi and pi, right? Then, what's the log of z? The log of z is going to be the log of r, that's the real part, plus I theta, okay? So where do your imaginary parts reside? The image over here, so your theta, your v basically, is going to be theta, and that's going to be between negative pi and pi. Great. And then what does the log of r do? Well, r can be anything between 0 and infinity, right? So the u is the log of r, and that's anything between what? That's anything between negative infinity and what? And infinity, right? If we had small values, so in other words, what's happening over here is, let's think about some of these images over here. So in other words, what you're doing is you're mapping to the strip. So in other words, what the log does is the log maps this region over here onto this strip. There's pi, that's the imaginary part of z equal pi. Dot over here, that's the imaginary part of z equals negative pi. And that's your strip, like so. Excellent, okay? So in other words, the log maps this slit complex plane onto this strip over here. Good. Let's look at some specific cases of this though, okay? What's the specific case? So what's happening? So let me draw, for example, this sort of circle over here. Let's look at this circle over here, like that. So this green circle over here, I'm going to parameterize that as r e to the I theta, where theta is between what and what? Where theta is between negative pi and pi, right? And let's say that r is less than 1, right? So let's suppose that r is less than 1, okay? So what's going to happen over there when r is less than 1? Well, what's your u going to be? Your u, in this case, is going to be the log of r, and that's going to be a negative number, right? Less than 0. So your u is going to be negative, and your v is going to be what? And your v can be anything. And v is just what? It's just between negative pi and pi, okay? So in other words, your negative numbers come from over here. So these green circles get mapped to this strip over here, right? So your real part is constant, so you're over there somewhere, right? That's where that circle is going to be. If I do this one over here, let's look at this circle, a big circle. That big circle over there is going to be rho e to the I theta, where here, of course, theta is between negative pi and pi. And now rho is bigger than 1, right? And so that forces u to be the log of rho to be greater than 0, right? And v is still stuck in where it belongs, right? And theta. Okay, so those big circles get mapped to these strips down over here, like that. Okay, so what's the upshot of this? The upshot of this is that log z maps the interior of the disk, interior of the slit disk, unit disk, onto what? Onto the strip, onto this region, I'll call this region omega over here, which is the set of z such that the imaginary part of z is between negative pi over 2, negative pi and pi. And the real part of z is less than 0. Okay, so in other words, if I just truncate it, I break it into two parts. So the slit unit circle goes where? The slit unit circle goes to this half semi-infinite strip, right? And then the exterior of the unit circle gets mapped where? The exterior of the unit circle gets mapped to this other half strip over here. So I see exactly the structure of how this logarithm is acting as a conformal map, right? So in other words, I want to sort of lean into the properties of exponentials. So what I'm really doing here is I'm looking at sectors, right? I'm looking at different sectors. And now I'm able to sort of get more interesting components if I want to have a slit in my conformal map, right? So there's lots of complex analysis problems that involve saying, well, if there's a slit in the region, you better make a branch cut. Branch cuts will induce a slit, which you can therefore rotate, and you can therefore turn those slits into strips. You can take those strips and turn them back into half spaces with exponentials or LFTs, right? So we're going to combine LFTs, exponentials, and logarithms to get wide classes of different conformal maps that have slits in them, right? It will also allow us to do square roots. It will allow us to do square roots in inverse trig functions and the whole monty of different type of conformal maps in that setting. Thank you very much.